How?
Optimizing beta-carotene nanoemulsions using ultrasonic homogenization. Hey everyone! Welcome back to our channel. Today, we're diving into the fascinating world of food science, specifically focusing on a study that explores how to optimize beta-carotene nanoemulsions using ultrasonic homogenization. Sounds complex? Don't worry, I'm here to break it all down for you in a way that's easy to understand. First off, what is beta-carotene? It's a natural pigment found in many fruits and vegetables, and it's the reason carrots have that vibrant orange color. More importantly, it's a precursor to vitamin A, which is crucial for our health. It helps maintain good vision, supports our immune system, and even plays a role in skin health. But here's the catch: incorporating beta-carotene into food products can be tricky. You see, beta-carotene is not water-soluble, and it can degrade when exposed to heat, light, or oxygen. This is where emulsions come into play. By creating oil and water emulsions, we can encapsulate beta-carotene in a way that makes it more stable and bioavailable. In this study, researchers aim to prepare beta-carotene nanoemulsions using mixed surfactants without any co-surfactants. Surfactants are substances that reduce surface tension, allowing oil and water to mix more easily. The researchers used a technique called ultrasonic homogenization, which uses high-frequency sound waves to create tiny droplets of oil and water. Now, let's talk about the experimental design. The researchers used response surface methodology, or RSM, which is a statistical technique that helps optimize processes by evaluating the effects of multiple variables. In this case, they looked at three independent variables: surfactant concentration, ultrasonic homogenization time, and oil content. They set specific levels for these variables, which you can see here. For example, surfactant concentration ranged from 2.64% to 9.36%. By experimenting with different combinations, they were able to find the optimal conditions for creating the most effective nanoemulsions. One of the key outcomes they measured was droplet size. Smaller droplets can enhance stability and bioavailability. The researchers found that increasing surfactant concentration and homogenization time led to smaller droplet sizes, which is a good thing. Next up was the pianisidine value, which is an indicator of oxidative stability. Lower values mean better stability, and the researchers found that the right balance of surfactant concentration and homogenization time could significantly lower this value. Finally, they looked at beta-carotene retention. This is crucial because we want to ensure that the beta-carotene remains intact and available for our bodies to use. The study showed that the right emulsifying conditions could lead to impressive retention rates. So, what were the optimized conditions? The researchers found that a surfactant concentration of 5.82%, a homogenization time of 4 minutes, and an oil content of 6.5% yielded the best results. They validated these findings by comparing predicted values with experimental results, and they matched up quite well. This study is a great step forward in food science, especially for fortifying products with beta-carotene. It shows that with the right techniques and understanding of emulsification, we can enhance the stability and bioavailability of important nutrients in our food. Now let's explain the experimental design, specifically focusing on two powerful methodologies: the Plackett-Berman design and the central composite design, or CCD. If you're interested in optimizing processes, especially in fields like food chemistry, pharmaceuticals, or any area involving complex formulations, this part is helpful for you. Let's start with the Plackett-Berman design. This design is a statistical method used primarily for screening a large number of variables to identify the most significant factors affecting a response. Imagine you have many ingredients or conditions you want to test, but you're limited on time and resources. The Plackett-Berman design comes to the rescue. Rationale: the beauty of this design lies in its efficiency. It allows researchers to determine the impact of multiple factors with a minimal number of experiments. This means you can save time and resources while still gathering valuable insights. Design resolution and aliases. In a Plackett-Berman design, we typically encounter resolution 3. This means that while we can identify the main effects of our variables, they may be confounded with two-factor interactions. For instance, if we're looking at surfactant concentration, it might be aliased with the interaction between homogenization time and oil content. This is something to keep in mind when interpreting results. Now, let's talk about the design space. For our example, we might consider a surfactant concentration ranging from 1 to 5% W/W, an ultrasonic homogenization time from 2 to 10 minutes, and an oil content that you would define based on your specific needs. Power. The power of the design depends on the number of replicates and the magnitude of the effects you're studying. Screening designs like this one prioritize detecting main effects over interactions, which is perfect for our initial exploration. Now, moving on to our second design, the Central Composite Design, or CCD. Rationale. The CCD is particularly useful when we want to fit a quadratic model, explore the response surface, and optimize key factors that we identified during our screening phase. It allows us to estimate curvature effects and interactions, giving us a more nuanced understanding of how our variables interact. In terms of design space, we can set specific points for our factors. For example, surfactant concentration, 1 to 5% W/W, with low at 1%, center at 3%, and high at 5%. Ultrasonic homogenization time, 2 to 10 minutes, low at 2, center at 6, and high at 10. Oil content. This would also have defined ranges based on your specific formulation needs. The design points will include axial points, factorial points, and center points, all crucial for a comprehensive analysis. Next, let's discuss how to analyze the responses. When analyzing the data, we start by selecting a model. In this case, we'll fit a quadratic model and use ANOVA, that's analysis of variance, to identify significant terms. We'll check metrics like the R-squared and adjusted R-squared values, as well as the lack of fit to ensure our model is adequate. Diagnostics. We'll also use residual plots and normal probability plots to validate our model assumptions. This step is critical to ensure our findings are reliable. Finally, we can generate 3D surface plots and contour plots. These visual tools help us visualize the relationships between our factors and response variables, making it easier to understand how changes in one variable might affect another. Now, let's wrap up with the optimum factor settings. To find the best conditions for our responses, we'll use the desirability function. This function helps us combine multiple responses into a single metric, allowing us to identify the optimal settings that maximize or minimize our desired outcomes. And there you have it. Today, we explore the Plackett-Berman design for screening variables and the Central Composite design for optimizing those variables. Both methodologies are invaluable tools in experimental design, helping researchers and practitioners make informed decisions based on statistical analysis. If you found this video helpful, don't forget to like, subscribe, and hit that notification bell for more insights into the world of experimental design and optimization. Thanks for watching, and we'll see you in the next video.
Pharmaceutical.